Good? All right, so today this is going to be the replacement lecture for the class we missed for hurricane-induced weather. So we are going to start today in section 5.5, and we're going to be looking at RL circuits. And then we're going to go to section 6.1, chapter 6.1, the very beginning of RLC circuits. And we're not actually going to do any solutions for RLC, but we have a little bit more to do with initial conditions with RLC. So we'll do that. I think in the interest of time, so I'm going to mention a few things here. I'm not going to do any of the derivations that I did last time for the RC circuits, because everything is, as you would expect, works about the same. So remember, so let me just come over here and let's just remember, for RC circuits, one resistor, one capacitor in series, and we have an equation for V sub C of T. And what do we need to know for that? We need to know its initial condition wherever it starts. We need to know its final condition, which is the path that it starts on. So you turn the voltage up to 10 or 11. I wonder if anyone will get that reference. You turn it up to 11, and then the capacitor begins to charge. It's on the path towards 11. It doesn't know if it's going to turn off early or not, but it's on the path towards 11. And then lastly, we need an RC time constant, Ka equals RC. And then finally, we'll end up with an equation, V sub C of T, and it's going to include all of those things. And it will be an exponential with some starting point. And then lastly, we're going to have U of T. Remember, U of T is the step function that says, let's be a little bit more general, before T naught, nothing happens. And then after T naught, it just is multiplying by 1. So it's just a way of helping us write piecewise more quickly. So rather than having to say T less than T naught is 0, if I just multiply it by U of T minus T naught, that does that for me. Okay, so let's come over here to RL circuits. It's going to be dramatically the same, in the same sort of opposite way that we've been doing this. So we are going to look at a circuit with one resistor and one inductor, and it's going to be in parallel with a current source. So this is our basic. If we don't have the current source, then we have the natural response. If we do have the current source, then it's the forced response. Remember that the natural response, the equation for the forced response includes in it the natural response, because it ends up simplifying to that when we have the natural response. So again, so natural versus forced. Just leave it on here. Okay, natural versus forced. And then another distinction I want to draw as well that we will kind of talk about as we write the solutions. So natural means no source. Forced means source. We also have something called transient versus steady state. Transient means changing, so it's what happens in the initial part when the part is changing. Steady state is your DC. It's where you're headed towards. Okay, so this part is the part that's changing. That's going to be your exponential. And steady state is your constant. So we can divide each solution into either natural versus forced. Forced has to do with the source component, and natural is the rest. Or transient versus steady state, transient being all the exponential part, and steady state being the constant. So we can just divide each one either way. Yeah.
Are they two separate entities?
Yes, so we divide them two different ways. Yes. Yeah. Okay, so let's then, I'm just going to go ahead and write out the equation for this. I'm going to write out the equation then for, and so here, this is one resistor, one inductor in parallel, compared to one resistor, one capacitor in series. Here we can find V sub C first, because it cannot change. So we know something about right after the voltage, input voltage changes. Over here, what stays the same? I sub L. So here we have an equation for V sub C. Here we have an equation for I sub L. The equation is identical. with the exception that it's current and our tau is equal to L over R. Yes?
So for our circuits, let's say that if we have a power source, so
What do you mean power source? You need to tell me
the
current or
voltage, so voltage source.
This one is for a current source in parallel with one resistor and one inductor.
Could
So
we source
if-
transform to?
Depending on what you have. If you can, this is the only condition for which the following equation I'm going to write is going to work.
Okay.
Just like this one only works for one resistor, one capacitor in series with a voltage source. So any other setup, you either need to rederive the differential equation or you need to work it into one of these. Okay, so let's write down what the equation is. So again, we're finding I sub L of t. So it's going to be final value. Actually, yeah, I'll write it that way. Plus how far I have to go times how fast it is to get there. And then all of that, oh, let's be more general, sorry, let's be more general. So it's the same equation as we wrote for V sub C. It's just it's I sub L, final, plus how far you have to go, times how long it takes to get there, all of that times this, which says it's only when that starts, when my current source starts. Okay, so let me see if there's anything else I want to say. So that means then it's the same processes that we have for RC circuits. So that's why I don't mind this class being one that we miss, because this is, we're going to kind of do everything the same way. So the first thing we're going to do is find I sub L at its starting point. And we're going to find that from our initial condition circuit before the switch was thrown. Then we're going to draw a new circuit. And we're going to call that our response circuit. So after the source is turned on, we'll look at the response circuit. Also from the response circuit, we get tau. So the only thing we get from the initial condition circuit is our initial value. Everything else comes from the response circuit, so same process. Draw your initial, get your initial. Draw your response circuit, get your other pieces of information, drop it into the equation. Okay, so let us do some problems. Yeah, was that? Oh, yeah, I do need to erase. Good point. Good point. All right. I'm glad I have an audience. Okay, so here's our first example. So here's our circuit. We need to find several things. I can't get it all on the board at once. So what we need to find are our initial values. And again, we're always looking for the initial value of what doesn't change. For RC and RL, it doesn't make any sense to find the current through the capacitor before the switch is thrown because it's going to change. So there's no point to doing that. So all of our zero minuses are going to be only the things that don't change. I sub L, V sub C. And then after the switch is thrown, we want to know what those are. It should be the oh, I'm sorry. I sub L and V sub L. So we know I sub L doesn't change. That will be the same, but this will be different. And then we're going to look at the final. We're going to find current first, and then we'll find voltage. Okay. So let me just write in some numbers here. So here's our circuit. So R sub 1 is equal to 30. R sub 2, 120. R sub 3 is 60. And L is 0.2. The voltage is 12 volts. Okay, so that's the circuit we want to solve. Okay, so the first thing we're going to do is find, we're going to draw our initial condition circuit. So this is for t less than 0. And we assume that this has been in place a long time. The switch has been a long time in position 1 for a long time. So in position 1 for a long time, we just have the following circuit. And again, importantly, if we define voltage plus minus, the current is in the direction of the voltage drop through all of our components that are source power recipients, so resistor, capacitor, and inductor. Okay, so if I look at this, I'm trying to find the initial current. What do I know about the initial converter? If this has been in place a long time, there's no source, must be zero, nothing's happening. So I know that I sub L of 0 minus is equal to 0 amps. What's the voltage at that time? Same thing. And also I can think about this, if this has been in place a long time, another way I can draw that is like this. Remember, an inductor is essentially a short when it's been in place a long time, because V is L d I dt. If I is not changing, then voltage is 0. So for this reason also then I know that my voltage, 0 volts. So this is A. Okay, B says what happens right after the switch is thrown. So right after the switch is thrown, I know what this one is. I sub L stays the same. V sub L changes. So let's draw our new circuit. So here's B, so this is at t equals 0, or t, I should say, greater than 0. Oh, you can't see it, sorry. There it is. Okay, so we know that I sub L of 0 is still 0. But now, right after the switch is thrown, we need to, so this is in the moment, right after the switch is thrown, there's no current flowing through here. So it means I just have this. So that's a voltage divider. So I'm looking at 60 divided by 90, that's my voltage here across my inductors, my voltage across my resistor. So because the current is 0, I know that V sub L of 0 is 60 over 90 times 12. 8. Yep, which equals 8 volts. And that's just due to voltage division. Okay, again, we don't need this value. We're not looking at V sub L. We can use that later when we find our equation for V sub L and check it, but this is not part of our finding the equation, because what is the first equation I'm trying to find? Always I sub L, the thing that doesn't change. So what else do I need to get from this then? This is my response circuit. So I need to know what happens at infinity. At infinity, that means it's been in place a long time. This becomes like a short, which means all the current is going to go that way. So if we want to, if it's helpful, go ahead and draw, we can think of drawing a t equals infinity circuit. And I should pause for a moment here. Taylor brought up a good question before, which is pertinent here. I told you that the equation we were going to use is for when we have a current source in parallel with one resistor in parallel with one inductor. Not what we have. So we can do a source transformation. That would be certainly a good way to do it. Or, dare I say, I can think of that as a Thevenin. We went there. So Thevenin means what is the open, if this were not here, then this here would be my open source voltage. That's the voltage division, so 8 volts, I already know that. And then these two, if I found R Thevenin, right, I deactivate the source. So R Thevenin would be 30 in parallel with 60, or 20. I think it's 20. So V Thevenin is V open circuit is 8. R Thevenin is then 30 in parallel with 60. That's 20. And then I need to put that into a parallel current source, so which would in fact be a Norton equivalent, right? So this would be V over R. So 0.4 amps. I know I'm off the page, I will fix that. Where do I have a space? There we go. Okay, so then I have a new circuit. So I can draw my last circuit this way. And actually, it would be perfectly suitable to do this in the very beginning. When I first drew the circuit here, that's probably the time to do this. When I first drew my response circuit, that is the time to go ahead and put it in the proper form. Okay, so this is a short. So here I have 8 volts. No, it's a current source. So we have 20 here. Again, I sub L is still defined that way. This is a current source of 0.4 amps. So all of this was to say, I'll fix that up, that's a current source. So all of this is to say, then what is my final current through my inductor?
0.4.
0.4, because it's all going that way, it's a short, which makes sense. It's just like the voltage across the capacitor charges to the maximum voltage, the current through the inductor charges to the maximum current that you have access to. So we finally know then that I sub L of infinity is equal to 0.4 amps. I'm off the page, let me get a new page so we can finish the problem. All right, so we know then, I'm just going to summarize what we have so far. I sub L of 0 is equal to 0. I sub L at infinity is equal to 0.4. The last bit we need is tau, which is L over R, which in this case is, what was L? Oh, and this is important then. The R that we're using is the R from this circuit. We have to get all the way down to here to have one R and one L. So we're going to have L, which was 20, L was 0.2 Henry. There we go. 0.2 Henry over 20 ohms, so 0.01. Okay, so now we have enough to write our equation. So I sub L of T is equal to where we're going to finish, plus how far we have to go, 0 minus 0.4, times how fast it takes to get there, and then all of that U of T. So again, this is I sub L of infinity plus I sub L of 0 minus I sub L infinity, how fast it is to get there, and then all of that times U of T. Okay, so cleaning it all up, 0.4, 1 minus e to the minus t over 0.01. Okay, once we have that, that's what we always find first, then we can find v sub L of t is just L di dt. So let's go ahead, I'm going to go ahead and write that answer. I'm not going to do the work for you. I'll fill that in. So this ends up being 8 e to the minus, and would it be all right to write it this way? 100, yeah. So divide by 0.01 is the same as multiply by 100. It doesn't matter which one you write. Sometimes it's easier if this is an easy number to write. We tend to write it this way because then it's clear to see what time scale we're on. If you write it this way, you just have to do a little mental gymnastics to find that. So we can check then. V sub L at 0 plus should fit in this one. I put 0 here, I get e to the 0 is 1, I get 8, that's what we have. Okay. So upshot is the process, the equation works just exactly like RC circuits. The difference is it's I instead of V, it's parallel instead of series, it's current source instead of voltage source. Okay, so let's do another one. All right, so here's this one. We'll fill in the numbers. So 12 ohms here, 10 ohms here, 40 here. I'm just going to write off to the side, L1 equals 1 Henry, L2 is 2 Henries, is not the problem that I have next. Hang on a minute. We want to do this one next, sorry. We want to do this one next. My apologies. All right, so here's the circuit we want to do next. We don't want to look at 2 inductors just yet. So R1 is equal to 6. R2 is equal to 12. L is equal to 2 henries. And the source current is 4 amps. And the switch closes at 1. Now we have 2 switches. One switch closes at 0, and one switch closes at a second later. So we're going to have then multiple different scenarios. The first one is before t is 0. The next one is from t equals 0 to t equals 0.5. And then a third piece is going to be after 0.5. So for each piece, you draw a new circuit. For each piece, you have a new starting point and a new ending point. So for each piece, the equation you find is only good for that time segment. Okay, so let's start with that. So I guess that's our first circuit here. I'm going to redraw. So I'm going to redraw. So here is t less than 0. So when t is less than 0, this switch is open and this switch is open. So what must be the current through the inductor?
0.
Nothing, because it's not connected to anything. All right, so I don't even need to draw that circuit. I'm just going to say I sub L at 0 minus is equal to 0 amps. Because it's just not at all connected. Okay, so now we have t greater than 0. When t is greater than 0, let's take a look at our original circuit. When t is greater than 0, this switch closes, this switch is still open. So that means this resistor is not in play, only these 3 branches. Okay, so that one's going to be pretty easy. It's already laid out for us in the form that we need. So what was this? 4 amps, 6 ohms, and 2 henry. Okay, so what do we need from this? This is our response circuit for our response to the first thing that happens. So this is our first response circuit. So we're going to write an equation for this. So we need initial, final, and top. So initial doesn't change. So we know that I sub L at 0 is still 0. I sub L at infinity, this is the path that I'm set on. So when I connect to a 4 amp source, the inductor immediately begins charging towards that. It does not know that a half a second later its life is about to change. It doesn't know that. It gets on the path towards 4 amps. So we know that that's its final value because in the end, when this has been in place a long time, the inductor acts like a short, so all the current will flow through the inductor. 4 amps.
Sorry, so when it's closed for a long time?
When this switch, the one that's closed at t equals 0, we're going to assume it's in place a long time. So if we can let it run until everything stopped, then eventually all the current would be going through the inductor. All right, so Ta is L over R, so that's 2 over 6. I know I'm always telling you guys not to write everything in fractions, not to write anything in fractions. I'm going to leave it this way because I know I'm doing divided by Ta. So if I divide by a third, I'm just going to multiply by 3. That's going to be an easier thing to do. Okay, so now I have everything I need for that equation. So we have I sub L of t. My starting point here is 0. So I'm going to have my final value plus how far I have to go times how fast it's going to be to get there. This is t over Ta. T over 1/3 I'm going to write as 3t. And then this whole thing. Should I write u of t on this one? I'm thinking no. And the reason for that is I know from the problem setup, this is only going to be good for 0 to 0.5. If I didn't have that second switch, I would add a u of t because it says it's good from 0 to infinity. But in this case, I know that's not true. So in this case, I'm going to say that this is good for t between these values.
So only include u of t when it's...
That means from here to infinity. And so if I'm not going to infinity, I can't do that. Okay. So this is actually good that t greater than 0, but really when t then becomes greater than 0.5, now both switches have been thrown. So here, this we're not writing u of t, because u of t suggests this. And we know that that's not true. Right, so it's not good for that long. So now we need to look at what happens when the second switch is thrown. So let's just come back up here and look at our original problem. When the second switch is thrown, I'll have I in parallel with R, in parallel with L, in parallel with a second R. So I'm going to have two resistors, so I'm going to need to fix that before I can do anything else. So here is our t greater than 0.5 seconds. So you just draw it all out. And our resistors are 6, 2, 12. Okay, so clearly we have an easy thing we can do here. Sorry about the focus. We can combine these two resistors, 6 and 12 in parallel, no problem. So we're going to combine these two. 6 in parallel with 12, I believe, is 4. So that means we're going to have, I guess I'll go right here. My current source has not changed. So I have the correct type of circuit. One current source, one resistor, one inductor, all in parallel. So the first thing I need to do is figure out what my initial current is. I can't tell that from here. I need to go one circuit back. One circuit back is here. I need to find out where I was at 0.5 seconds. So where I was in the previous circuit at 0.5 seconds, I just need to plug in. So I'm just going to plug in 0.5, I'm going to get a number. That's my ending point here, which is my starting point in the next piece. That's how I keep my current definition continuous from one piece to the next. Okay, so that means that, and I'm going to write it this way, I sub L of 0.5, this is my new starting point. And so that comes from my previous equation, which is 4 times 1 minus e to the minus 0.5 times 3. And that turns out to be 3.107. Oops, sorry. So what that means is, in the previous circuit, in 0.5 seconds, I had enough to charge. I didn't get all the way to 4 amps. That's where I was headed, but I got up as far as 3.1. So that's my initial value. My final value I can get from this. In the end, what's my final value? Where is this current headed towards? Full 4 amps. So it's got the same final values it did before. That's fine. And then tau. Tau has changed as well. Okay, because now I have more resistance in the circuit. So now I have L over R, so it's going to be 0.5. Okay, so now I can write the equation again. So now I've got I sub L of t is equal to final minus how far I have to go, plus how far I have to go, how long it takes to get there, and then this is good for t greater than 0.5. Right, so let's clean it up and write everything all together. Yes?
Shouldn't the t be t minus
Yes,
0.5?
thank you, absolutely, absolutely, yes. This should be t minus 0.5. Yes, thank you. Thank you, thank you. Because what the important part about this exponential is that it starts at the starting point. So if without the 0.5, I put 0.5 in, I get t to the minus 1. That's not my starting point. My starting point has to be t to the 0. Right. Okay, so let's write down then our final answer. So